this video, we're going to look at friction, drag, and stopping distances for different types of objects. The learning intentions for today's video are to explain the effect of drag on an object's motion, and investigate the effect of friction on the stopping time for an object or a vehicle. So firstly, have a look at all of these pictures and tell me what do you think they all have in common. There's probably a few different answers here. Have a quick chat with your partner and see what you can come up with. What is the common pattern between all of these pictures? You may have come up with a few different answers. The main one I was looking for is that all of these things are optimized for aerodynamics in some way, or flight or movement in some way. We're going to look at that. We're going to look at what we mean by this aerodynamics and how these things are optimized. So firstly, we're going to consider free fall. If gravity is just constant acceleration downwards, it means it's acting on everything that has mass to pull down. The acceleration due to gravity is 9.8 meters per second squared, and this is used for any free fall situation as that A value. So if we ever see an equation that has A, or we represent acceleration as A, and we're going to look about that in a lot more detail in a later video, but that is just 9.8. This does, however, ignore air resistance. So as I've mentioned previously, we always talk about this concept of an isolated system in physics, where we assume there is no such thing as air resistance. However, in aspects of this video, we are going to consider what happens if there is air resistance, because we cannot have drag without air. So in the last video, we looked at forces and balancing forces. Air resistance is that unbalanced force that acts to oppose the motion of an object when it moves through the air. It's often referred to as drag force. So air resistance and drag force are the same thing. Drag force is really just the actual force, or the technical name used to describe air resistance. Drag can act in all directions, and basically it's caused by an object moving through the air particles, and those particles are hitting the object and providing some resistance. The faster you get, the more particles you hit, therefore the more drag that you experience. As an object slows down, the drag force decreases, and when you're not moving at all, you're not colliding with any air around you, so you have no amount of drag force. The drag equation is quite complex. You're not expected to know or use it, but it is this equation here. So drag is half the coefficient of drag times the area, or the cross-sectional area of an object, times density. This is the Greek symbol rho, which means density, times the velocity squared, or the speed of the object squared. So what it means is the amount of drag that you feel, or an object feels, say a plane flying through the air, is a product of its coefficient of drag, which is just a value assigned to an object based on its shape. So for example here, if we had a block, its coefficient of drag would be 1.28, which is pretty bad. As we go to more and more aerodynamic shapes, so a triangle, a cylinder, an ellipse, and then the airfoil, which we've seen in our last video, we decrease the coefficient of drag down. So it's interesting to know that in this case, the cylinder and the ellipse aren't actually the same. You might just think having a curved surface creates a more aerodynamic surface, which it does, but you see it's not that much different to just having a triangle where the air is hitting the flat side of it. The ellipse and then the airfoil are far more ideal to reduce these kinds of drag. Then you also consider the cross-sectional area. And what we mean by this is if you looked head-on to the object, how much area does it take up just in that direction? So if you were to sort of slice it front-on, that's the amount of air that it's hitting. That's the only part we care about. We don't care about how long the object is, because those parts of the plane or the car or whatever it is aren't actually hitting the air. We care about the density of the medium, as in the air itself, because the more dense the air is, the more particles there are to hit, therefore that'll increase the amount of drag on you. And lastly, we care about the speed, because the faster you're moving, the more particles you're hitting, therefore the more drag force that you would experience. In the last video, we looked at plane designs, and I mentioned this concept of biomimicry, about where we model nature to create these amazing engineering things. This is a really good example of a bullet train and how we use this principle of biomimicry to optimize the plane in nature.
In 1989, Japan's Shinkansen bullet train had a problem. It was fast, really fast, like pushing 170 miles per hour fast. But every time it exited a tunnel, it was loud. The noise was coming from a variety of sources, but whenever a train sped into a tunnel, it pushed waves of atmospheric pressure through the other end. The air exited tunnels with a sonic boom that could be heard 400 meters away. In dense residential areas, that was a huge problem. So an engineering team was brought in to design a quieter, faster, and more efficient train. And they had one secret weapon. Eiji Nakatsu, the general manager of the technical development department, was a bird watcher.
Different components of the redesigned bullet train were based on different birds. Owls inspired the pantograph. That's the rig that connects the train to the electric wires above. Nakatsu modeled the redesign after their feathers, reducing noise by using the same serrations and curvature that allow them to silently swoop down to catch prey. The Adelie penguin, whose smooth body allows it to swim and slide effortlessly, inspired the pantograph's supporting shaft, redesigned for lower wind resistance. And perhaps most notable of all was the kingfisher.
The kingfisher is a bird that dives into water to catch its prey. The unique shape of its beak allows it to do that while barely making a splash. Nakatsu took that shape to the design table. The team shot bullets shaped like different train nose models down a pipe to measure pressure waves and dropped them into water to measure the splash size. The quietest nose design was the one modeled most closely after the kingfisher's beak. When the redesign debuted in 1997, it was 10% faster, used 15% less electricity, and stayed under the 70 decibel noise limit in residential areas. And it did all that with the wings of an owl, the belly of a penguin, and the nose of a kingfisher. There's a name for design like this. It's called biomimicry.
The people who design our world usually never take a biology class, believe it or not. So they're novices in how the world works.
That's Janine Benyus. Back in 1997, she wrote the book that coined the term biomimicry. It told the story of the innovations in computing, energy, and health that were inspired by structures in the natural world.
Stick like a gecko, compute like a cell, even run a business like a redwood forest.
Benyus has since worked as a consultant for various companies, trying to get them to understand how to take design ideas from nature. That might mean studying prairie dog burrows to build better air ventilation systems, mimicking shark skin to create bacteria-resistant plastic surfaces for hospitals, or arranging wind turbines in the same drag-reducing pattern that schools of fish swim in.
So that's a great little video to help you consider when you're designing tasks. Is look for an example in nature that can be applied. Look for a living thing that does that sort of application and look at what it does, how it's built, how it functions to optimize that. Now we're going to look at this concept of terminal velocity. We looked at it last lesson when we saw the skydiver with the drag force being pulled, but I just want to recap it. Ultimately, terminal velocity is the limit of how fast an object can fall. Velocity is basically a speed, so terminal velocity means the maximum speed that something can fall. It all depends on the amount of air resistance of the object. As we saw in the earlier thing, drag has a lot of different effects on an object, and when those forces are balanced, so the drag force pushing up and the gravity pulling down are balanced, you have reached that maximum speed. You cannot accelerate any more than that. In theory, with these equations, if we drop a feather and a bowling ball at the same time, they should hit the ground at exactly the same time as well. In the real world, this doesn't happen because there is an effect of drag on those objects. But if we take the air away, that does happen. There's lots of great videos where we'll see dropping different objects at the same time. They'll hit the ground at exactly the same time. Now we're going to look at reaction time and how it applies to moving objects.
Evan, there's been a lot of changes this offseason for your team. How do you feel your chances are in the AL East?
I love our chances. You know, it's been... Guys, keep it on the field. Guys, keep it on the field.
So now what we're going to do now is a quick little reaction time activity. So this is a great way to test your reaction speed. So what you're going to do is you're going to grab a partner and a ruler. And you are going to hold the ruler in the air from one end of the ruler. And your partner is going to hold their fingers right at the bottom of the ruler. with 2 fingers apart. At random, you are going to drop the ruler and they're going to try and catch it as quick as possible. Then you look at where their fingers landed on the ruler to look at that measurement, and we're going to take that distance as the S that we've got in this equation. We need to convert it to meters. So for example, if I caught it at 11 centimeters, that's 0.11 meters. I've already done some of the rearranging for you and made this equation easier, but basically what you do is you do that experiment. If you want to do it a couple of times to get an average, you can, but your reaction time is the distance on the ruler converted to meters divided by 4.9, and then take the square root of that number, and that is your time in seconds for your reaction time. So you can just use a calculator for this, it's nice and easy, but have a go at that with a partner, record your reaction times, and we'll use that information as we go on. So the average human reaction time is 0.75 seconds. There are different reaction speeds depending on what the stimulus is. So for example, touch is quicker than hearing and sound, because to hear and see something, you need to absorb that information. So your eyes need to see it, your ears need to hear it. That information goes to your brain. Then it goes, all right, this is what we need to do, and it sends the signal to your body. Touch is much quicker. Your senses on your body are faster than your brain processing visual and auditory information, so touch is quicker. But on average, the reaction time is 0.75 seconds. This becomes really interesting because if we consider you're driving along at 60 kilometers per hour, which is 16.6 meters every second, how far would you travel in 0.75 seconds? That's just the time it takes you to even react, not even to do anything. So have a go at that. See if you can figure out how far you would travel. If you're moving at 16.6 meters every second, and it takes you 0.75 seconds just to react. So we can work it out using a couple of different equations. You don't need to know what these equations are yet, but it's just the velocity, how fast you're traveling, times the time that you're traveling that speed for. So in this case, I've converted kilometers per hour to meters per second already for you. I just times it by 0.75 seconds because that's how long it took you to react. You've traveled 12.5 meters. So probably close to the length, if not double the length of the classroom, just in the time it took you to react. You haven't even put your foot on the brake yet. So that's kind of scary. Let's look at a table of stopping distances. This table here gives you braking distance on a dry road versus a wet road. We would expect the friction to be much less when the ground is wet. We cannot stop nearly as quickly. It also gives you the reaction distance, so how far you travel in the time it takes you to react. Where it gets really interesting is if we look at something like 60 versus 70 kilometers per hour, you're talking 25 meters to 29 meters, almost 30 meters stopping distance. So just by increasing your speed a little bit, it takes you almost 5 meters longer just to react. Almost another classroom length just in the time it takes you to realize you need to stop. If we consider the overall stopping distance, we're talking sort of 54 meters in wet road, 45 meters in dry road, versus 56 meters, so 11 meters further to stop in total, just by moving about 10 k's further. So that's pretty concerning in terms of the risks of speeding. Let's consider a speeding to work case. Let's say you're late to get to school. Instead of doing the speed limit, which is 60 kilometers per hour, you speed and travel at 70 kilometers per hour. If school was 25 kilometers from home, how much time do you actually save by speeding? And in this question, if you wanted to, you can convert to meters per second. You can probably just stick with the units we've got because you've got kilometers per hour and you're told a distance in kilometers. It's entirely up to you. If you want to convert to meters per second, remember you just divide the number by 3.6 and that gives you meters per second. But have a go at this. I want you to calculate how much time you're actually going to save by speeding. I'm going to assume you've done it. This is the answer. So we would work out, don't worry about the equation. You've done it however you've done it, but we're going to figure out that if you were not speeding, it took you 25 minutes to get to school. 1500 seconds if you converted, or 25 minutes. If you were speeding, it took you 21.4 minutes. So really, when you look at the difference there, it is very minimal. You shaved off about 4.6 minutes by speeding, and in the previous slide we just saw how much you've increased your stopping distance. If someone was to step out in front of you, a dog ran across the road, whatever, your chances of stopping are so much less for just 4 minutes to get to school every day or to get to work, whatever that scenario is. That we can see ultimately that speeding is just not worth it. So to recap, can you explain this term of drag and its effect on objects in a very general sense? And can you explain the effect of friction on an object's stopping time? And here we're more talking about simple things like discussing how increasing the speed increases your stopping distance, and how we've got this concept of reaction time affecting how far we travel as well, so a reaction distance. See you next lesson.